A sprinkler head has to open when there's a fire, a flame detector has to spot that fire quickly, and a security product has to resist an attack for long enough to make a difference. But how do you know any of them will actually work when conditions stop being convenient? That's what we're here to find out inside the LPCB test facility. We're going to see 4 very different tests: a sprinkler head exposed to fire, security products subjected to physical attack, a fire alarm sounder tested against electromagnetic interference, and flame detectors challenged by a controlled fire. Because a data sheet can tell you what a product is designed to do, these tests show what happens when reality pushes back. First up, fire suppression. The sprinkler head itself is purely mechanical. There's no detector loop deciding whether smoke has reached a threshold. No software logic is needed to operate the head, and no fire alarm interface is required to make it open. But the test still needs to be repeatable, measurable, and consistent. The facility creates a controlled fire using a crib with a known energy output. 3 thermocouples monitor what happens. 1 is positioned directly in the fire, 1 is positioned at the sprinkler head, and 1 is placed 3 meters away to measure how the heat is spreading through the space. Inside the sprinkler head is a glass bulb containing a liquid designed to expand as the temperature rises. Once the sprinkler reaches its operating temperature, the glass bulb shatters. That releases the valve, and water is discharged directly over the area affected by the fire. And no, when one sprinkler head activates, the entire building doesn't suddenly become a water park. Each head operates independently. Only the heads exposed to enough heat should open. The actual fire suppression is mechanical, but proving, monitoring, and integrating that system very quickly becomes part of the wider electrical and life safety installation. The sprinkler may sit alongside monitoring switches, flow switches, pump controls, pressure switches, fire alarm systems, and building management systems. So the head may be mechanical, but the wider installation still needs to know what has happened. Seeing all the fire testing actually reminded me of something. We have our own MI cable, which is LPCB approved. Next, we move from fire to physical security, and this one is brutal. Products such as fence panels, a steel box with timber lining, and a roller shutter door are professionally attacked under controlled conditions. The tools, the methods, and the time periods are all defined because anyone can say a product is secure. The question is, secure against what? At the lower end of the test, the tools are basic hand tools. The sort of things someone could carry easily, conceal easily, and use quickly. As the rating increases, so does the level of threat. Larger mechanical tools and battery-powered tools are introduced. The rating achieved depends on 2 key things: what tools were used and how long the product resisted the attack. Given enough time and enough tools, almost anything can eventually be defeated. So security is not necessarily about stopping someone forever. It's about slowing them down enough to make the attack difficult, noisy, risky, or simply not worth the effort. And does that delay give enough time for detection, response, or intervention? A strong enclosure, shutter, or barrier doesn't just protect property, it protects the installation, the people maintaining it, and in some cases, the supply. The important thing is that the test produces a measurable level of resistance against a defined attack. Secure is not an absolute condition, it is a performance claim against a specific threat. And it's important that these sort of products are put through the testing because look, you don't want people messing around in there. The next test looks like something from a science fiction film. This is an anechoic chamber. The walls, ceiling, and floor are lined with specialist absorbers designed to stop reflections and reduce background interference. That creates a controlled test environment. The product under test is a fire alarm sounder, and this is important because the real world is electrically noisy. You've got radio signals, mobile phones, Wi-Fi, switching power supplies, drives, contactors, LED drivers, inverters, and all sorts of other equipment producing electromagnetic interference. Inside the chamber, an antenna emits radio frequencies towards the sounder. The aim is to check whether the device continues to operate correctly while being exposed to electromagnetic interference. Does it false trigger? Does it stop working? Does the sound output change? Does the electronics behave as expected? That's what this test is trying to prove. EMC can feel like one of those hidden subjects. You don't always see it. You don't always hear it, but when things go wrong, it can be a nightmare to fault find. False alarms, random failures, comms errors, unexplained resets, devices behaving differently on site than they did on the bench. It's not enough for a device to work in perfect conditions, it has to keep working when it's installed in the real world. If you are finding this information useful, we dive into topics like this every week, so hit subscribe. That is why EMC Testing Matters. It gives confidence that when a fire alarm device is installed in an electrically busy environment, it still does the one job it absolutely must do. Operate correctly when lives may depend on it. The final test is a really interesting one. These detectors are not looking for smoke. They're not simply waiting for heat to build up, they're looking for the radiation produced by a flame, specifically ultraviolet and infrared radiation. That makes them suitable for large or open areas where traditional smoke detection might be too slow, too difficult, or simply not suitable. Think warehouses, fuel storage areas, industrial sites, processing plants, aircraft hangars. Anywhere early flame detection is critical. The test is carried out indoors under controlled conditions. That allows the engineers to assess whether the detectors can identify the flame and respond as expected. And that response matters because in these environments, a fire can develop quickly. The detector needs to see the flame, distinguish it from the surrounding environment, and communicate an alarm to the wider system. But the product is only one part of the equation. The final performance also depends on the installation, where the detector is positioned, what it can see, and whether anything obstructs its field of view. A detector can perform perfectly in the test facility, but it still needs to be correctly installed and maintained if it is going to provide the same protection on site. A sprinkler head exposed to a controlled fire, security products subjected to physical attack, a fire alarm sounder exposed to electromagnetic interference, and flame detectors challenged with a controlled flame. The tests are completely different, but they are all trying to answer the same question. Will the product still perform when it really matters? A data sheet tells you what the product is designed to do. Testing shows whether it can keep doing that when exposed to heat, fire, physical attack, or electromagnetic interference. And the final result still depends on how the product is installed, integrated, and maintained. That's where the claim meets reality.